I'll create a more developed script that reaches 16 to 18K characters while maintaining depth and narrative flow. Why nothing can break the speed of light. Einstein's universe revealed. Most people think the speed of light is just a cosmic speed limit, like a highway sign posted at the edge of the universe, 186,000 miles per second. Don't exceed it. Laws of physics. End of story. But that's not what it is at all. The speed of light isn't a restriction placed on the universe by some cosmic legislature. It's a revelation about what the universe actually is, about the fundamental fabric of reality itself. Understanding why nothing can exceed light speed requires us to abandon almost everything we think we know about space and time. It requires us to see the universe the way Einstein saw it, not as a static stage where events unfold, but as a dynamic, interconnected entity that bends, stretches, and transforms in ways that challenge our deepest intuitions. Let me take you on a journey that starts somewhere unexpected, with Isaac Newton, a falling apple, and the moon hanging in the night sky. The foundation. Newton's insight. In the 1600s, Isaac Newton made a connection that changed everything. He observed that objects fall consistently, predictably, dropping 16 feet in the first second every time. This wasn't random, it was law. Then he looked up at the moon, seemingly floating in defiance of this very law. But was it defying gravity, or was something else happening? Newton had a profound realization. The moon is falling. Right now, constantly. Every second of every day, the moon is plummeting toward Earth. It's just moving sideways so fast that it keeps missing our planet. That's what an orbit actually is. Perpetual falling combined with enough lateral velocity to keep missing the target. Think about that for a moment. The moon isn't held up by anything. It's in free fall, just like a dropped apple. The only difference is its sideways motion. Newton then asked a revolutionary question. What if gravity weakens with distance? Not just a little bit, but according to a specific mathematical relationship, the inverse square law. Here's what that means. The moon orbits about 240,000 miles from Earth's center. We stand on the surface, about 4,000 miles from the center. The moon is therefore 60 times farther from Earth's center than we are. If gravity follows an inverse square law, it becomes weaker by the square of the distance. At 60 times the distance, gravity should be 60 squared. That's 3,600 times weaker. Newton calculated how far the moon should fall toward Earth in 1 second at that reduced gravitational strength. He took the 16 feet that objects fall here on Earth's surface and divided by 3,600. The result? About 1/20th of an inch per second squared. He then calculated the moon's actual fall rate based on its orbital period and distance. The numbers matched perfectly. The moon was falling at exactly the rate Newton's inverse square law predicted. This wasn't just elegant mathematics. This was prediction. Newton had connected two completely independent observations, how fast apples fall on Earth and how the moon moves through space, with a single universal law. The implications cascaded. If this law was correct, planetary orbits should be ellipses. And they are. Kepler had already measured this but couldn't explain why. Newton explained it. Tides, the shape of planets, the motion of comets, all suddenly made sense under this one framework. One law, multiple predictions, all confirmed by observation. This is how science builds certainty. The first crack, rumor and the speed of light, fast forward to the 1670s. Astronomers were studying Jupiter's moons with ever-increasing precision, making detailed observations over months and years. And they discovered a problem. The moons weren't keeping to their predicted schedule. Sometimes they appeared 8 minutes early, other times 8 minutes late. 8 minutes. That's a massive discrepancy. Had Newton been wrong? Was the law of gravitation flawed? Ola Roma noticed something crucial. The moons ran ahead of schedule when Jupiter was close to Earth, and behind schedule when Jupiter was far away. The pattern was consistent, repeating with Jupiter's position. Roma had an audacious idea. What if light takes time to travel? What if what we see when we observe Jupiter's moons isn't happening now, but happened in the past? However long it took light to travel from Jupiter to Earth. When Jupiter is closer, light arrives sooner. When Jupiter is farther, light takes longer to reach us. The moons weren't running early or late, we were seeing them early or late depending on light's travel time. By measuring these timing discrepancies and knowing the distances involved, Romer calculated the speed of light. He didn't measure light directly. He measured it by trusting Newton's law so completely that any deviation must indicate something else at work. This is profound. One solid scientific law becomes the foundation for discovering another. The avalanche had begun. The strange behavior of light. Once you know light has a finite speed, you can measure it more precisely. And when you do, you discover something that should shatter your understanding of reality. Light always travels at the same speed. Always, no matter who measures it, no matter how fast they're moving. Stand perfectly still, shine a flashlight, measure the light speed. 186,000 miles per second. Now get on a spaceship, accelerate it to half the speed of light, shine a flashlight forward in the direction of your motion. Common sense says the light should now travel at the speed of light plus your speed. Just like throwing a ball forward from a moving train makes the ball move faster relative to the ground. But measure the light. It's still traveling at exactly 186,000 miles per second relative to you, not faster. The same speed. This should be impossible. Velocities are supposed to add. If you're on a train moving 50 miles per hour and you walk forward at 3 miles per hour, you're moving 53 miles per hour relative to the ground. That's basic physics. That's common sense. But light doesn't obey this rule. Light's speed doesn't add to your speed. It remains constant. Accelerate your spaceship to 90% of light speed. Measure again. Still 186,000 miles per second. Push to 99.9999% of light speed. Measure once more. Still, impossibly stubbornly, the exact same speed. By the late 1800s, physicists were deeply troubled by this. Experiments kept confirming it, but it made no sense within the existing framework of physics. Einstein's revolutionary leap. In 1905, a 26-year-old patent clerk named Albert Einstein confronted this impossibility head-on. Instead of trying to explain it away, he asked a more fundamental question. What if our basic assumptions about space and time are wrong? We assume time flows at the same rate for everyone, everywhere. We assume space is rigid and fixed, the same for all observers. We assume these things because they match our everyday experience. Einstein said, what if none of that is true? What if time and space are flexible? What if they bend, stretch, and compress to keep light speed constant for all observers? The mathematics worked. Einstein showed that if you accept the constancy of light speed as a fundamental principle, then time dilation and length contraction must follow as logical consequences. When you move fast relative to another observer, time literally passes more slowly for you. This isn't an illusion or a measurement error. Clocks actually tick slower. Biological processes actually slow down. Time itself is different. And space contracts in your direction of motion. Distances actually shrink. These effects are tiny at everyday speeds, which is why we never notice them. But as you approach the speed of light, they become dramatic, undeniable, measurable. The universe bends the fabric of space and time to preserve light's constancy. This is special relativity. Why there's a limit. The resistance of space-time. Now we come to the heart of the question. Why can't anything exceed the speed of light? Here's what happens when you try to accelerate an object. At everyday speeds, it's straightforward. Apply force, the object accelerates. Apply more force, it accelerates more. But as you approach the speed of light, something strange happens. The object becomes harder to accelerate. Its resistance to acceleration, its inertia, increases. This isn't because the object is gaining mass in the traditional sense, though that's a common simplification. It's because the relationship between energy, momentum, and velocity changes at relativistic speeds. As you get closer to light speed, adding energy produces less and less additional velocity. You're not hitting an engineering limit, you're hitting a fundamental limit of space-time itself. At 90% of light speed, accelerating further requires exponentially more energy. At 99%, even more. At 99.9%, the energy requirements become astronomical. As you approach 100% of light speed, as you approach the speed of light itself, the energy required approaches infinity, infinite energy for infinite resistance. You can't reach light speed because you can't access infinite energy. The universe won't allow it. Light itself travels at this speed because photons have exactly zero mass. They have no resistance to overcome. They must move at light speed. It's not a choice for them. They have no other option. But anything with mass, any amount of mass at all, can only approach this speed. Never reach it. Never exceed it. The deeper structure, space-time as a unified entity. Einstein's next insight went even deeper. In 1907 and refined through 1915, he developed general relativity and revealed something more profound about reality. Space and time are not separate entities. They're not independent dimensions that happen to coexist. They're woven together into a single, four-dimensional fabric, space-time. You exist in space-time. You move through space-time. And here's the key. You're always moving through space-time at a constant rate. Always. But that motion is divided between movement through space and movement through time. When you're sitting still, not moving through space at all of your motion is through time. You're aging at the maximum rate, experiencing time at 1 second per second, marching into the future as fast as time allows. But when you start moving through space, you must divert some of that motion away from time. You're now moving through both space and time, which means you're moving through time more slowly than before. The faster you move through space, the slower you move through time. These aren't separate effects. They're two aspects of the same underlying reality. There's a maximum to this trade-off. If you could move through space at the speed of light, you would have diverted all your motion into spatial movement. You would have zero motion left for time. Time would stop for you entirely. This is why photons don't experience time. From a photon's perspective, if we can even use that phrase, it's emitted and absorbed in the same instant. No time passes in its reference frame. The universe is frozen. You can't exceed the speed of light because you can't have less than zero motion through time. You can't move backward through time, at least not in any way that makes physical sense. That's the wall. That's the absolute limit. Reality confirms Einstein. This isn't abstract philosophy, it's not speculative theory. Every prediction of relativity has been tested exhaustively, and every test confirms it. Particle accelerators routinely push subatomic particles to 99.9999% of light speed. And every time the same thing happens, the closer the particles get to light speed, the harder they become to accelerate. The energy-to-velocity relationship matches Einstein's equations perfectly. GPS satellites orbiting Earth travel at high speeds and experience weaker gravity than we do on the surface. Both effects cause time to pass differently for them than for us. The satellite's clocks run at a different rate. If we didn't correct for relativistic time dilation and gravitational time dilation, GPS would accumulate errors of several miles per day. The system only works because we account for Einstein's predictions. Cosmic rays strike Earth's upper atmosphere, creating particles called muons. These muons are unstable and decay rapidly. Their average lifetime is about 2.2 microseconds. At that lifetime, even traveling at nearly light speed, they shouldn't reach Earth's surface before decaying. But they do reach the surface, many of them. Why? Because they're moving at relativistic speeds, time slows down for them. From our perspective, they live longer. From their perspective, the distance to Earth's surface is contracted, so they don't need to live as long. Either way you calculate it, using time dilation or length contraction, more muons reach the ground than classical physics would predict, exactly as relativity requires. The ultimate answer. So why can't anything exceed the speed of light? Because the speed of light isn't fundamentally about light at all. It's about the architecture of space-time itself. Space-time has a maximum rate at which cause and effect can propagate, a maximum speed at which information can travel, a maximum rate at which forces can act, a maximum velocity for change itself. That rate, that universal constant, is what we call the speed of light. Light travels at this speed not because light is special, but because photons have zero mass, and therefore must travel at the maximum speed space-time allows. If light didn't exist, the speed limit would still be there. It's built into the structure of reality. Einstein revealed that space and time aren't the stage where physics happens. They're participants in the drama, flexible and dynamic, responding to energy and motion. The limit isn't imposed on the universe from outside. The limit is the universe, its fundamental geometry, its deepest structure, the continuing avalanche. From Newton watching the moon fall and unifying Earth with the heavens, to Romer timing Jupiter's moons and discovering light's finite speed, to Einstein reimagining the nature of reality itself, each insight built upon the previous one. Each breakthrough opened new doors. Each answer generated new questions. That's the avalanche that began 400 years ago, and it's still accelerating. We've used Einstein's insights to detect gravitational waves, ripples in space-time itself. We've photographed black holes, where space-time curves so severely that not even light can escape. We've confirmed that time passes at different rates depending on gravity and motion. The speed of light is the key that unlocked space-time, and space-time revealed a universe stranger, more interconnected and more beautiful than anyone imagined. Not comfortable, not simple, but true. And that truth continues to avalanche forward, carrying us toward discoveries we can't yet imagine.